Hello everyone, this is Vagatube, and today I'm estimating the instantaneous rate of change. So, to do this, what we're doing is making some sort of graph to say y equals x cubed plus x squared, so that looks something a bit like that, except it does pass through the origin and go up weirdly, but don't tell them on that. And so we're estimating, say, the gradient at this point here, the rate of change at that point. So, to do this, so that point's 2, what we often do is estimate the secant between this point, say 1.9, and then the distance between those 2 points, the average rate of change between those 2 points. Get a fairly rough idea, good idea of what the rate of change is going to be. So in this case, so if we're using this example, so if we've got the average rate of change, as you know from my last video, is y1 minus y2, x1 minus x2. So to figure this out, so y1 is obviously y equals 2 cubed plus 2 squared equals 12, and y2 equals 1.9 cubed plus 1.9 squared, which, the closer this point is, so if you do 1.99, you get a much more accurate estimate. We're just using 1.9, so 19 cubes, 6,859, so 6.859 plus 19 squared is 361, so 3.61, and that adds to be 10.469. Please correct me if my maths is wrong. So, what we do to figure this out, to estimate the average rate of change, so y1, so 12 minus y2, 10.469 on, we've got x1 is 2 minus 1.9 equals, what you call it, 1.5, braining, 531, I hope, on 0.1, which is the same as 1531 on we've got 100. So we've got our pretty good estimate of our average rate of change. So we know it's about so it's about, because I'm not even sure if that's right, 15.3 is our estimate of our average rate of change. So that's approximately the gradient of that point there. So that's how you calculate or you estimate your instantaneous rate of change. Now, leading on from this, next video I'll be showing you how to get a much more exact method of this using first principles. So thanks for watching. This has been Vagatube, and see you next time.